Okay, good, 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 good. We've been into the assemble technique. Last class we had our experience with the practical session for decision tree and random forest, right? So we already did that, and so the reason why we had to do that session is because most of the ensemble technique methods build up using decision trees. And after that, now we had a discussion in the group. I don't know how many persons followed the discussion where Best man was explaining how smart comes in to affect the integrity of your model. I don't know if you all followed that discussion. It was an interesting one. And he proved that if you use smart on your data set before splitting into test and train, it's going to lead to data leakage. And so the recommendation was that you split your data into train and test before using smart on the train data set. Madam Pierre, welcome. At least we have you around now. We have been waiting. So that was a very interesting one there, Bestman. I don't know if you can hear me. You are surely in the high sea somewhere flying in an engine boat, but if you can hear me, that was a good one there to prove the fact that smart, because we know that smart is just it's an approach that we use to balance, to handle imbalanced data. And
Prof,
we are
we
looking at
can't get
situations where,
you.
oh, you cannot hear me?
Yes, Prof.
No, I was talking about smart. I don't know if you can hear me now.
Yes, it's okay now.
Okay, I was just talking with respect to the discussion we had with Best Man in the group where he did that analysis to prove that when you use smart to handle imbalanced data before splitting into train and test, it affects your model due to data leakage. And so it's better to use smart on your train data set after splitting the data into train and test, and then you use the original data set to test the model after it's done. So that's what I was saying, that was actually a good approach when it comes to um handling data leakage as far as uh that is concerned. But then I still look at that approach because this is a discussion I ignited with one of my profs just to understand something. Because the idea is we are just having this discussion because it's a brainstorming. I don't know. I would have really loved that Best Man is available because I'm just
Hello,
wondering
good evening,
because,
Prof. I'm available.
oh, thank
Sorry,
God,
I'm
thank God
coming
we are.
late. Sorry.
Yeah, it's fine. It's fine. Let's quickly talk about smart before we jump into Adaboost today, okay? Because I was looking at the situation, right? The different approaches to balancing data. Okay, let's look at the situation where we have 100 records, for example. And inside these 100 records, 95 were known cancer, say no cancer, and then 5 were cancer. This is clearly a case of imbalanced data. Now, if we are trying to avoid data leakage, what we have to do is that we have to split this data set into train and test, and then we apply smart. We apply smart on the, which one is it? Is it smart? We apply, is it OT? Is it SMOTE? We apply smart this thing, on the train data, and then we use that train data to train the model. Now, like I was asking my prof, when I was looking deeper into these small things, I was asking him now, if I do that, if I split this data that I have now into train and test, there is a probability that if I split this data into 20, let's calculate what's 20% of 100 is what? Is 20 records now? 20
Yeah,
records.
20 records. Yeah.
Yeah. There's a probability. It's very possible that these 20 records that I have for test and 80 records for training, there's a probability that all these my 5 records here can end up in my test data. Is it possible? It's possible, right?
Yeah.
It's possible that all my 5 records can end up in my test data. And so my question to him was, if in that case, why then would I need to use SMART again? Because I thought the idea of using SMART was that we wanted to make sure that the model during training was able to see all the various categories that were available for our data during training, so that we can now be able to use that trained model to predict. So I don't know, Mesma, maybe you have an idea into how all of that plays in, but I was just researching and looking into that.
Yeah.
But
It's a bit noisy, but I am about to talk if it's manageable.
yeah, I think we can hear you.
Okay.
We can hear
So
you.
I think the idea is that for this level, 5 level, which is a category, it has its distribution. So there's a distribution to it. The distribution defines what is the mean for that category that is 5, that has 5 units in the data set. So when you use SMART will create replication of this 5 to average it, to make it 95. That means it will make 90 of it. It's going to make 90 of this 5 to make it 95,
Yes.
95 each balance. Okay.
Yes.
So in this instance, now you notice that this SMART, when it does its own synthetic data, it builds it more on the mean of that 5 category. So the 5 category, the variance on the 5 category out of that 95, that which is total, to be low. It has low variance. That means the data is concentrated in the mean. So it has to have more weight than the initial 95, where there was a spread, of course. So it's the mean of the new synthetic data, which will now overwhelm the previous one. Now create the same problem, wherein this synthetic data which you added, which is 19 total, are heavier on their mean. That means the model will train more on them than the other 95, which is spread. So it's the difference in the variation that will not cause a problem to the model. That makes the model bias on it. So the point in which you introduce them is also important. In the last problem we did, I don't know if I would have loved to bring up my graph to see what I was trying to say, because we are trying to solve
just explain. I'll take it from there.
We are trying to solve a problem of imbalance data for
imbalance data,
like,
yes.
now
yes.
we will not disadvantage the previous one by making synthetic. When the difference is too much, when you now make the synthetic of it in such a way that it is 90 out of, you're adding 90 synthetic data to 5 to make it 95. And the synthetic data, the distribution of synthetic data is not well spread. That means the variance is very low. It's within the mean.
Yes.
And so it's not make this category now, let's say 5 is a category. So to make that category heavier, so the model will change, will have more weight on it, will now be biased towards it. And that is where the issue, that now reverses.
Now, my question is, according to the recommendation of using SMART, right, to avoid the situation of data leakage, because that is a recommendation when you're looking at the best practices of SMART, right?
Yeah.
It is recommended that you use SMART on your training data set. I don't know if you have that understanding too as well. I mean, I had that because it was stated that you should split your data into train and test, and then use SMART on the train data set. I don't know you get it.
Let me look at my argument that day, because I haven't forgotten. I think it will be...
your argument is valid. I understand the distribution around the mean, and then because the variance is small around the non-cancer category, the cancer category, sorry, because we use SMART to get the synthetic data. Normally the variance will be small because we'll be using the existing values and then using the mean to generate all the other synthetic values. That's completely clear. That's clear, because that's how SMART works. I mean, this is, to me, it's just a question that I'm just processing in my head, and I was trying to find out.
I don't know the question you're asking. Yes, I don't understand the question. You're talking
again,
about...
I'm saying that I'm looking at the use case of SMART. When to use SMART? At what stage?
I think SMART will be useful. Okay, I think there were two arguments for whether before the splitting and after the splitting. I think that was the difference between what
Yes, that
we're
is what,
talking
that's
that
where
day.
I'm getting, that's where my interest is, right? I'm more interested in around that use case when before splitting and after splitting. You understand? Because like I'm
Yes.
asking, if my data is 95.5, for example, and I take 2080, for example, and I split this data into train and test, there is a chance, I'm not saying that it's all possible, but there is a chance that all these five can end up in the test data set. And according to the recommendation, I'm expected to use SMOD on the 80 balance that is left, which is the data that I'm going to use to train the model. So
I
I'm
think that
asking,
day you did split it before the smart.
before
That's
the
what you
SMOD,
did.
yes.
Yes. Me, you splitted it before the smart. You have to do the smart before splitting so that the
No,
smart
that day
will
I think, did we
yeah.
SMOD before splitting or we split before SMOD? Because I remember the only thing I did was I changed the X, I identified the X, which is the I think I can pull up that practical session again. Because I mean there is a certain challenge around that which I was looking into. And I was also reading into some documentation. It's good that we have that discussion. Wait, let me pull that thing up. I have a lot of notebooks open. I don't. This is that kind of stuff. Champions badge. No, this is not the champions badge. I know. Let me come back here. Science weekend champions badge. That was on the practical of decision tree, right? It should be here.
Hello, Prof. Hello?
Has he? Have we? I think he has left. So,
Okay, this network.
Bestman, which day I go reach in 11?
You you will get there now. So like me, I'm looking at it from the statistics. The model that defines the problem. If you don't look at it from the statistical point, you're not going to see why it is behaving like that. Because if you go and train on slots, if you go and split before, if you split and apply slots, the
Yeah,
model. Okay,
let
it's
me
back.
let me features and target, because here we are specifying the target and here we are specifying the features X and Y. And so I use SMOD on X and Y before splitting X and Y to train and test, right? And again, this is actually not good because it's going to introduce data leakage, like you pointed out. I don't know, are you getting me?
Please come back. I didn't get that part. Next, I didn't get
I'm
your
saying
last.
that
Mm-hmm.
I'm looking at this, right? We use
Yeah.
SMOD on the features and the target before
Yeah.
splitting it into train and test, right?
Yeah.
This is where I used it. I used it on X and Y before splitting
Yes.
splitting that data into train and test. This is where I actually
Yes.
split the data into train and test, right?
Yeah.
After I've applied SMOD on the data set.
Yes.
And my third line was that because when we did the value count initially, for example, look at this category 3, right? Category 3, there is a high probability that if I do 80-20, there is a very high probability that these 3 might not even end up in my train data set because there are only 10 values. They might all end up in the test data set. It's possible. And the training will not see this category, which is 3. You understand? Because they were just 10 records. It's possible that the 10 records can fall within the 20% that I'm using for testing. And so if I just do like that, that means my model will not see the category 3 for during training. And so that is the reason that in my third line, I said, okay, if that is the case, then if you apply smart, it's going to redistribute that data and it's going to be good. But then it brings in and then that's where you have this, right? That's when we did that. And then after that now, before we split the data into train and test, now I'm sure that there is that in my training data, in my training data and in my test data, I'll have all the categories there. From 5, 6, 7, 4, and 3, I'll have 8. I'll have all these categories in my training data because I've balanced the data, right? I'm looking at my top line. And so that's when I split the data. But then it still brings in the issue of data leakage, which we're trying to bring about. And again, I'm looking at the way smart functions. And so that's where my worry line is. I don't know if you can pick the.
I think it's a bit looking at it. I have lost some of my thought process, but looking at it now, you are assuming that when you do the random split, that because the data point for certain category is small, that they will not be captured.
Yeah.
But we don't know the algorithm that does that, because the algorithm will try to pick each data point, each category, to have a distribution, a representation in the train and in the test.
That is a good thought point. So I have to look.
It's only in the cross-validation when the cross-validation is larger than the data point. That's when it will throw an error that this data point, if the data point is, let's say, it's 10, and you are doing cross-validation of 15, you tell that you cannot cross-validate on all because it has just 10 data points, and the algorithm will throw an error. Okay. Other than that,
again, I'll have to look into this.
Yeah,
it's good to look into how this guy works.
It will share it accordingly to each category. There will be a representation, because one, you know that some categories in the data, it's thought that they are not widely distributed, and they are, maybe let's say, what's the probability of seeing a man and a child in a day? A man, you can say a man 10 times, you can say a child 2 times. If you go and do smart on that data, you now make child to be 10 times as man. When you know that on the street you see more men than children, you are going to imbalance. The model will be such that it is not going to reflect the reality distribution of the category. The actual category is that we normally see 2 child on the street and 10 men, but it's looking like the category of men and a child is imbalanced because man is 10, child is 2. If you want to split the data, the category, each data point will be split to in this instance is so small. But the point I'm saying that the splitting of the data is such that each category is represented in the training and the test. And the data points too might also be a reflection. It might be an issue of the data quality, or it might be actually the distribution of the data that is used to predict the various categories. So you're not increasing one and leaving the other one low. When you know that the one you're increasing, you're going to be increasing it in a synthetic way, such that if you mean, because the synthetic, this smart, you look at the algorithm, it's more like averaging out things. So it's averaging out, to average the mean. So that synthetic data, if it's so small and you are making it, maybe say it's 5 and you're doing 90, you want to add 90 to 5. It's going to have mean of, and maybe say, let's say, it's going to take the mean of it. Since it's taking the mean, the average of it, that means that data will be more weighty than the other one that has a larger variance, larger spread in its distribution, in terms of its Gaussian distribution than this one. So I don't want to start giving numbers. If I can give numbers, let's say.
No, it's fine. It's fine. You raised a point there. That makes sense. There is a point you raised. Because because depending on how this works, if this works based on categories, like if you are sending in a categorical variable and splitting the 80-20 is per category, then it will be a nice thing. That's what I don't know, which I have to verify to be sure that that's the case, right? If that's the case, then it's nice. That means if it's splitting based on category, that means if I send a category like this, if I send these categories like this, that means it will take 2080 of this, 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 and 2080 of this.
Yeah. We can even verify it if we call that split function.
Yeah, that's what I'm saying, that I'll check it out.
Shift tab, we give you the documentation under how it is done, how it is run, the mathematics behind it. Shifter will do it.
Yeah, I should
Yeah,
be
yeah.
able to verify that and know, because if that's what it's doing, then it solves my problem. That means applying smart on the training data is way more, is of course the thing. But that was the recommendation. But but it didn't answer my worry, because the recommendation is that you apply smart after splitting into train and test. That is the recommendation. Okay, awesome. Let's look at Adaboost today. So I'll look into it again, and then in our next class, we'll have a discussion around what actually happens during the split and the train, and what is actually being picked, especially as far as categorical variables, a categorical target is concerned. Okay, great. Okay, let's come here today. Awesome. That was quite an interesting one, and it just triggers your brain to think in and out of the box around how some of these things are actually, function. So we just wanted to remind ourselves of the things we've said. We're looking at the ensemble techniques. Ensemble. We've talked about them. We talked about bagging. We talked about boosting. And we talked about stacking. Right? So we have already looked at bagging, where we looked at random forest, where we talked about bootstrapping, where we talked about bootstrapping and aggregation. These are the things we talked about here. Where bootstrapping is the situation where we talk about the random shuffling with replacement of the data set, random shuffling with replacement. Shuffle is double F, right? Shuffle with replacement. And then aggregation is just taking either the mean or the mode, based on the target, whether it's categorical or numeric. And so this is what we talked about under the bagging, which is an ensemble technique. Now, today we are going to be looking at boosting. And under boosting, we are going to be looking at three major, let me not just call them major, but kind of way. But we are going to be looking at three approaches or algorithms. The first one is Adaboost. The next one is going to be gradient boost. We're going to look at gradient boost tomorrow. And then the last but not the least, it's like a continuation of gradient boost, but it's called XG boost because it's an updated version of gradient boost. So it's not like it's a standalone algorithm on its own, but it's just an improvement on gradient boost, but it's mostly treated as an independent algo because it has its own framework. So today, let's look at Adaboost, this one, how it works. We look at the geometric intuition behind Adaboost, and then we see what are the different actors that come into play when you are dealing with that particular algo. Okay, awesome. And to think that I had, we're going through an interview session over the weekend, and we had some of these questions come up in that interview. Quite interesting though. Right, it was quite interesting. So let's look at boosting, and then we'll look at Adaboost. Now, before we go to Adaboost, let's remind ourselves again of the things we said during bagging. It's very important because we are going to draw inspiration from there to now look at the approach that has to do with boosting, right? Can I get some confirmation that I'm audible?
Yes, you are, Prof.
Awesome. Okay, let's start from bagging. We said we say wisdom of majority, right? We were looking at the wisdom of majority where we are using multiple models to make a decision, right? Multiple models. So now in bagging, which we were looking at random forest as the algorithm under bagging, we said we can have multiple models, and by default they are 100. So you have M1, M2, M3, and blah, 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 up to Mn. Now, we said that when you give it a data set like this, say that data set has 100 records, you split that data into 80, 20, for example, and then you send it the train data. This is your train data set. So this is your data set for training. So This is your data set for training. It takes all these records. This is sorry, this is your full data set, not sorry, this is your this is your full data set. It takes your full data set for training, and then it shuffles the data set and then gives to this man. A random selection now, it randomly picks records. Say they are 100, it can take the first 30, or it can decide to take 30 or whatever. It randomly shuffles the data and then train the different models. If they say with replacement, that means if it picks these records and used to train the first model, it goes and mix that data back. That's it replaces back and mix and then pick the next set and use it to train this one. Pick the next set and use it to train this one. So that's why we said in this, we are using all of these Argos are decision trees, but these use different data sets. Different data set. Because the data set that was used on this one is not the same data set on this one, it's not the same data set on this one, because the data set is being mixed and different records are picked and used during training. And that way, we said it's going to help the algorithm perform better. We already did a lot of explanation around that. That was the idea behind bagging, and that is what we refer to as bootstrapping. That was what we talked about. And that is the mechanism of action behind that particular algorithm. Now, let's look at, now when we come to boosting now, what is happening? What is happening? We still have the option of wisdom of majority. We are still using many multiple models. But now, how do these multiple models work? How do the plenty models work? So let's start. So let's say you have M1, M2, M3, and then we have up to Mn, whether they are how many, 1,000 models, 50 models, or whatever number. So we have model 1, model 2, model 3, and up to the last model. So in boosting in general, what is going to happen is that you are going to give this model one data set, your training data set. This model is going to train, let's take, for example, if it's a classification problem. If it's a classification problem, what this model will do is that it's going to do its own classification, and then the errors that this model have made or its own misclassifications is going to transfer those errors to M2. So when it's transferring, I'm calling it transfer. We are going to go into details and see how this transferring occurs. What do I even mean by transfer? So it's going to highlight the errors and then send it to model 2 and say, okay, I've done my own work. Focus on these ones. So model 2 again is going to do its own classification based on the errors highlighted by model 1 and then send it to model 3. Model 3 will do its own classification based on the highlighted errors from model 2 and then send it to the next model. And that is how it is going to go up to the last model that we have. And therefore means the errors here, if there were 2 errors here, when you get here, they might, if there were 4 errors here, here they might now reduce to 3, here they might reduce to 2, here it might, and then maybe at the end of the day, at the level of the last algorithm, the last model, we might just now have zero, close to 0, or the least number of errors should occur at that level. So that is boosting in general. Now, Adaboost, to be specific, has its own way of doing this job. How does Adaboost work? Okay, be thinking about it and then give me 1 minute. I'll be right back. Okay, I'm back. I don't know if you were all thinking, but I'm here now. Let's think. Let's go. So now, how does Adaboost does this, right? It's quite interesting. So remember, all of them are using the same algorithm and it's a decision tree. I already said this as far as the ensemble technique was concerned, we already had that agreement. It's a decision tree. So what happens is that Adaboost uses a decision tree, but this decision tree is a spatial decision tree. It's a spatial decision tree. What makes it spatial? You're not asking me what makes it spatial. It has it has just one split. Just one split. And this one split forms what we call a decision storm. A decision storm. Let me show you. I think I had, okay, good. Now, you know, for a decision tree, the way a decision tree normally functions is that when you give it data, it's going to keep splitting and splitting and splitting and splitting, right? Up until when you have only pure nodes. We've explained this a couple of times. But in this case, in the case of Adaboost, once it takes that training data, model one, the first model, will split that data only once. Let's imagine that way. This will be more, let's draw a scatter plot. Okay, let me draw a scatter plot. Let me draw a scatter plot like this. Assuming this is my scatter plot, and I'm going to have my data like this. Let me say I have my data like this. And then I have some data points here like this. Maybe like this. And then, okay, let me say this is my data. This is my data. So what is going to happen is that it will, the first model, which is M1, will do just one split. That means it will just split, it can give just one decision boundary here. And so when it gives one decision boundary here, these records have been cleared, have been well classified. These ones this way have been well classified because you can see they are all the same. But this one, there's a misclassification here because these records like this have not been well classified because they're in the wrong place. They were supposed to be this way, but they have not been well classified. So what is going to happen is that the algorithm M1 is going to highlight these misclassified records, highlight them, and then send the output to M2, telling M2 that this is where I had my errors. So you can pick it from there. Again, I'm making this very basic. We are going to go right down into the geometric intuition and see how this actually happens in real life, how they highlighting. I've not explained that, but just understand it from this high level that is what it does. It does one split, and that's why we are calling it a decision storm, because it's only one split that is done. I think that's the maximum depth is 1. So you just do the maximum depth. If you remember when we were going for decision tree, I think if we still have the decision tree classifier this way, okay, yes, we still have it. When you open the place where we say decision tree classifier, where did we call it? Just wait, I want to explain this before. Let me just run this. And then when I come down to, where did I call my decision tree classifier now? Should be somewhere, okay. If I do shift tab inside here, press okay, good. So you see that we have maximum depth here. It's maybe 1. The number of times you want to split. So the maximum depth is 1. So it just does one split, full stop. Okay. That is it. Let me clear. Am I supposed to clear? Okay, now, no, let me not clear. Let me come back to here. So once it does that now, that means it's going to highlight these ones and then send it to the next model. And then M2 is going to take it from there. M2 does its own classification. Maybe now M2 will come down. Maybe now what M2 will do is that M2 will now come and then put a decision boundary. M2 can now come and then put a decision boundary here like this. And if you put a decision boundary here, you see that this record has not been well classified. So it's supposed to be with this one. So M2 is going to highlight this one. And when they send it to M3, what M3 is going to do is that M3 is now going to put a decision boundary here. And then you see that everything is well classified now. Right? That is how the Adaboost in at the high level it works. Now, let's now go down into very details to see how this takes place. Remember, we only have a decision storm. It's a maximum depth of 1. Okay, I had this note prepared. So the idea here is that since this one does, and you remember we discussed this detail itself in if you split that data only once, it generates a situation of underfitting, right? Because it does only one split. It's underfitting, and therefore means that model M1, which splitted that data just once, will perform poorly. The performance will be poor because it did just one split. Data that it was supposed to split more than maybe 20 or 30 times, it did just one split. That means it's underfed, it's underfitting. It has not done, it has not been, it's not well splitted, so it's underfitting. And so, but that is how it's designed to work. And as we'll see how that takes into account. So that is automatically a situation of underfitting. That's why we refer to these models as weak models. So this is going to be a weak model. So the weak model, this will be a combination of weak models. So each model does one split. 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 So they are a combination of weak models to develop a stronger model. That's how it works, right? So now we have model 1, model 2, model right up to model MN. So so you have, this is an ensemble technique. So this is the process. The model 1 does is to work. Model 2, model 3, model 4. These are the models all in the line. So let's start. So it says boosting is a technique to build strong classifiers from weak learners in series. So I call them weak learners or weak models because they are just learning small in a series. And that's how it works. Each subsequent model works on the mistakes done by the previous model. So in this way, errors are reduced. That's just an idea. Why do we call them weak models? I've already explained, because it does one split. That's the maximum depth is 1. That's the decision to develop a decision storm. So I went ahead and I did some example here. So if you have data like this is the only split that happens. These ones have been correctly splitted in blue. But then these records like this have been misclassified. So what is going to happen is that this is M1. So this is what M1 does. So what M1 will do is it will put this decision boundary here. After pushing this decision boundary here, you will notice that these errors have been misclassified. So it will highlight them. It will highlight them. You notice that they are now bigger. It will highlight them and then give them to M2. So what is happening is that M2 will come then and try to classify these ones that M1 has highlighted again. And after classifying, you notice that these ones now too have now been misclassified because M2 was trying to classify what M1 had pointed out. And so once M2 does its own mistake, M3 now will come in trying to fix the errors of M2. And so it will do its own classification now. It will do its own classification, and all of that you will finally have the final model, which is going to be M4, which has done a good classification, and you have all your data points well classified. So let's because when I'm talking this highlighting now, you are wondering in your head, how does the highlighting work? So this is again D1, D2, D3, and then coming down to a final model. So these are the learners developing a stronger model. So here, weak learner is created. What is a weak learner? Whose accuracy is around 50%? Yeah, because when we say accuracy is around 50%, that means it performs poorly, right? Because it performs poorly. That's what we're looking at. So we should not look at, let's leave how prediction is done first, and then we focus on how the algorithm works. So let's assume that we have a data set like this. Please pay close attention. Let's assume we have a data set like this one that I have in my front. And so in this data set, what we are doing is that we are having data set, you have row number, you have gender, you have age, you have income, and then you are deciding this is the target. So these are the features X, and so this is the target Y, illness, to determine whether that person ends up with an illness or not. So this is going to be our target Y. So this is our record. Please, you have to be very attentive. If you have any question, please stop me and ask the question before we continue so that you don't get lost. So the first thing that the Adaboost algorithm will do, the very first step is that first, all of these data points will be assigned some weight. Initially, all weights will be equal. Let me explain. So this is your training data. So your data, let's assume that in our training data, we had 5 records. 1, 2, 3, 4, 5. This is an example of a training data. So what it's going to do is that it's going to assign weights to each record. What are these weights? So it's just going to be a proportion of the record. So this is 1 record out of 5. This record number 1. Record number 1 is 1 record out of 5 records. Record number 2 is 1 record out of 5 records. Record number 3 is 1 record out of 5 records. So if there were 1 million records in your training data, it would be 1 out of 1 million. But our training data has just 5 records. So that's why we are having 1 over 5, 1 over 5, 1 over 5. That is what we refer to as the weight. That's what we refer to as the weight. Let me wait. Is it clear? Who did not understand what I meant by weight? Who did not understand the concept of weight? Madam Pierre, you are quiet. Is everything going?
I understand it.
Oh, great, Mr. Tony, thank you. Madam Pierre came to class today, decided to mute herself, and is not saying anything. Oh yeah, okay, you're on your own. Let me go. Okay, awesome. That's the first thing the algorithm does, is that it's assign weights. That's step 1. Step 1 has been accomplished. So there's a formula for the weight, how it assigns the weight. Now, the formula to calculate sample weight is 1 over n. N is the total number of records. So 1 over n. So if there are 1 million records in your training data, it's going to be 1 over 1 million. So it's 1 over n, where n is 1, 2, 3, like up to the last record. So that's why we have sample weights 1 over 5, 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 1 over 5 for all the 5 records. Great. Next step. So I just explained that since we have 5 data points, so the sample weight assigned will be 1 over 5, of course. So here we have 5 data points, so the sample weight assigned will be 1 over 5. Again, I'm just reiterating. Now, step 2, we start by seeing how well gender classifies the samples, and we will see how the variable age, income, classifies the sample. We'll create a decision storm for each of the features and then calculate the Gini index of each tree. The tree with the lowest Gini index will be our first storm. Okay. Here in our data set, let's say gender has the lowest Gini index, so it will be our first storm. Again, this is just grammar. I'm going to go down and explain better. We will now calculate the amount of say or importance or influence for this classifier in classifying the data storm using this formula. Let me keep it here. Let me not go ahead and confuse you. Let me just scroll and go down. Forget about what is up. Let's go down to the data. Now,
The job is good though. We like the maths.
we are going to go back
The
to the
job
math.
is good though. We like the maths to give
We are
clarity.
going to go back to it. I wanted to come down to for the people who would better understand this thing as a result of visuals. Let's start from there. Then I'm going to go back to the math because the math is also important, because now you are seeing new. So the first step, we are done with step 1. So step 2, this is step 1 now. This is step 1. This is step 1, where we assign sample weight. Step 2 is that we are going to assign new weights. We are going to assign what? New weights to each record. This is where the math is now coming in. We are going to assign new weights to each record. So how do you assign a new weight? Okay, let's go up and see the formula for assigning new weight. How do you assign a new weight? Where's new weight? new sample weight. This is the formula for new sample weight. It says old weight times e raised to the power plus or minus amount of C. Amount of C is referred to as what? Alpha. Again, here, let me explain. You already know the old weight, 1/5. E, this is a constant. Plus or minus amount of C. This is the guy you do not know. Alpha. That's the person you don't know. So in this formula, the only thing that we don't know here is this one. So now the question is, how do you calculate this man? Is that clear? This man is the person they call the amount of C, or amount of influence. And we are going to see how this amount of C is important in the work that we're going to be doing. So again, we don't know how to calculate this. So how do we calculate the amount of C? Did I put the formula?
Prof, what is C? What is the definition of C?
Again, it's like influence, or let's say, again, I don't want to quickly rush to do it, because when I illustrate this and go down, you will see where alpha comes in and becomes a point. So it's like saying, just call it amount of C. Let's go down. I'm going to come back to it so that we don't confuse, we don't get it twisted. Let's just say amount of C, we call it alpha. Okay, let's go up. First of all, let's see what is this alpha and how it is calculated. That's what we call amount of C. What does it mean and how it is calculated? So how do you calculate? This is where we calculate. We calculate the amount of C, or what you want to call it, alpha or whatever. So this is the formula. Here, you have half log 1 minus. The only thing that we don't know here is what we call the total error. Total error. So now, we are going to take 1 minus the total error over total error. So what is going to happen is that, let me clear this. This is where we calculate alpha, okay? Now, we had, assuming in this, because I was saying that, assuming in this our data set, only one record was misclassified. Just assuming that M1 classified every other record. They classified this one well, classified this one well, classified this one, did not classify this one well, and classified this one well. So how many misclassification errors are there?
One.
One misclassification error, yeah? Is only one. So that's what we refer to as a total error. And what is the weight of that record that has been misclassified?
1/5.
So you start seeing where the weight comes in initially, because this weight is just a value which takes into account the total number of records in your training. So that's why I said if there were 1 million records in your training data, that would be the denominator, 1/1 million. So the records that have been misclassified, let's not forget our target. We want to point out how M1 will tell M2 that this is where I made mistake. Some way of saying that, like I call it highlight. Some way of highlighting the misclassifications. That's what we want to prove, how it does that. So let's focus. And then in the course of that, we are also going to be discussing a lot of things. So if we assume that this was the error that the record that has been misclassified in our training data by M1, because it did just one split, then let's continue and see how it's going to highlight this error. So the weight of that error is of that particular misclassification is going to be 1/5. If there were 2, we would have taken the total weight. So if there were 2 misclassifications, for example, it would have been 1/5 plus 1/5, right? Are you understanding? Okay, so let me clear all drawings. So let's come down. Let's say we have just one, which is point number 4. So that's where the alpha comes in. So that's the total error. So 1 minus total error over total error. And so the weight of our total error was 1/5. So here we are going to just do this by saying 1 minus Again, I've used 1/5 here because that's the weight of that record that was misclassified of the total error. Our total error was just 1, and so the weight is 1/5. That's why I'm saying that if we had 2 misclassification errors, we would have 1/5 total. What does total mean? Sum of errors, right? 1/5 over 1 over plus 1/5. We would have done the total like this. But in this case, we just pick 1 for simplicity, for the sake of simplicity, just to explain how it works. So it's going to, this is how they calculate alpha, or the amount of C. Is going to be alpha is calculated as half the log of E, 1 minus amount of error over 1 over the total error, which is 1/5. Again, is the same thing because 1 minus total error over total error. This is, so if we do all that calculation in this our case, we are going to end up with this alpha being this. Again, you can punch your calculator, take your calculator and begin to punch these things. You should end up with something. So now, what does it mean? So the total error will always be between 1 and 0 and 1. And that's true. Because see, if you take 1 over the total number of records, right? 1 over your total number of records. So, and then you, for each to get your weight. And so if you sum all of these, the denominator will always be your total number of records. Because if I have 1/5 plus 1/5, if I sum this for people who did small mathematics, the denominator here is 5. So what is going to be this? This is going to 2/5. Is that correct? 5 divided by 5. Is it like that? Is it 2/5?
Ultra.
Okay. So that will be the denominator. So your denominator will always be the total number of errors. So if all your errors, if so, in the case where you do all of this and you have 5/5, you have 1. If you have 0, you have 0, right? So that's it. So that's why I'm saying here that it will always be between 0 and 1. You cannot have it go out of that margin. Again, for my people who do not love maths, a quick highlight of what we have said. We want to calculate our new sample weight because in step 2, we are supposed to assign new sample weight. And the formula to calculate new sample weight is O weight multiplied by E plus or minus the amount of C, right? The amount of C. That is how we do it, right? So the question now is, what was this amount of C or alpha? And then we've shown you how to calculate alpha using the total error. Therefore means, in essence, what amount of C is a representation of the amount of error, or how much error that, or let's say is a representation of the errors or the weighted errors at the level of each record, right? And maybe just an example like that. Maybe I don't know, maybe I'm not using the right words, but when we go down again detailedly, you're going to understand that more clearly. Now, so let's come down to see how to calculate it. New sample weight. So let's come down to each record now. Each record, we are going to take let's start with the first one, record number 1, this one. So what was the sample weight? 1/5. So if you take, this is the O weight. If you want to assign the new weight, you are going to take this O weight and put it in this formula up here. So we are going to take the O weight, which is 1/5, multiplied by exponential. Now there's something here that's very important. You are going to multiply it by exponential amount of C, which is alpha, and we have already calculated alpha up here. And our alpha was 0.69. This was our alpha, which is the amount of C. Now, please, I want to explain something. If the record is correctly classified, you are going to use negative. If the record was wrongly classified, the algo will use positive. And so once it does its first split, when I say correctly classified, is if the first split that it does, that means it just creates one split. So as it's created that one split, it checks whether this split that I've done at the level of the category just gives me a pure node. That's what it means. A pure node means that it ends up as maybe yes or no. But if he has yes, 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 if that split has yes, yes, you people remember now. Well, let me just highlight it because for the sake of understanding, so that we don't get, because you are now asking me, how did he know which one? Remember, did we have that decision tree? Please let me pull up decision tree for weather. I think it was for weather, right? How do you spell that weather again? Weather data. Okay. Let me see if that decision tree exists. Decision tree example problem for weather data. Let me see that decision tree. I want to explain something to you so that you do not get it twisted. I want to see the tree. Did you plot the tree? This guy did not plot the tree. There's another link that plotted the tree. I think this link plotted the tree. Oh, yeah. Yes, I want to use. Network is slow. This thing is not loading. It's not loading my data. It's not loading. I wanted to show you the tree. I come back and I go straight to images. Should help me. Okay. So you see here that, like we were saying, like I was trying to explain, it does just one split. So it's all going to end here. It's all going to end here. It's going to end here. It's not going to split it again. And therefore means you notice that if it does just one split, the first split, boom, you'll notice that all the records that were overcast will be correctly classified because it will be a pure node. It will end as yes, right? And then all the other records, whether they were going to come this way or Sunny or whatever, they are now. So let's see how many were there. One out of these 14 records, I think overcast yes, there were around 3 of them. So you see that 3 of them will be correctly classified, and then the remaining, how many, 11 will be misclassified. So it's going to highlight. So now when it's adding and when it's using an alpha for each of these records, so these records are going to run 14. So when it's calculating, when it's going to be calculating the new weight, these records that have been correctly classified, because directly from here they are leading to a pure node directly. It's yes automatically, so there's going to be no split. These records, these 3, assuming there were 3 of them, their alpha will be negative. They will use negative for their new sample calculation, their new weight calculation. And these 11 that have been wrongly classified, they will use positive for their new weight calculation. Is it clear? Let's go.
Prof, please come again. Please come again.
Let me go back and illustrate here. Let me go back to the. Let me come back to the data set that we're working on. So let's see. Let me explain. Now, in this our record, we said that, assuming that in our example, only this record was wrongly classified, so all the other records were classified. So that means when we are calculating alpha, if the record is correctly classified, so you'll notice that the formula for calculating new weight is plus or minus. So the question is, when are you going to use plus and when are you going to use minus? So for the records that have been correctly classified, you are going to use minus, and for the records that have not been correctly classified, you are going to use plus. So in this our example, only record 4 was not correctly classified. So this is the only situation where we are going to use plus. So let's see. Let's come up. So to calculate the new weight for record 1, we are going to use minus. So 1/5 times exponential -6. So when you put all of this means exponential. If you are not a good math person, all of this evaluates to exponential. That's what we are saying, exponential. That's why EXP means exponential. And exponential alpha, what is alpha? Alpha is 0.669 because we've calculated alpha over here. This is where we calculated our alpha. And so which sign should you use? We are using negative because that record falls under the list of records that were correctly classified. So it's like saying the forecast. It's like saying that record was under outcast, for example. Overcast, sorry. Right? So that is clear that it's already a pure note. Let's just calm down. Let's just continue and then we see. So how many records were there? There were actually 5 records. And so if you do that, so the new, if you multiply all of this, you have 1.4. So for all the correctly classified, the new weight will be 0.1004. And then now let's look at the record that was wrongly classified. So now for wrongly classified sample, the update weight will be, so instead of using minus here, you notice we have not used minus here, so there's a plus. We have used plus, but in mathematics, it doesn't make sense to write plus 0.69. It doesn't make sense because by default the sign is positive. So that's why we've used 0.69 directly without the minus. If you notice here, we use the minus, but here we've not used because that is the record that was wrongly classified. And so since that was a record that was wrongly classified, when you calculate the new weight for that record, this is the value that you're going to have. Okay. That is clear.
I think I kind of get it. The alpha kind of models the error and scales the rate of decay. So if the data point is wrongly classified, it will increase the weight so that the model can give it more emphasis in training. That's what I see. That's why it is since it is
Exactly.
it is a rational number, so they have to make it negative because negative exponential, if it's a whole number, will decay. But since it's a fractional number, that means it will be the inverse. It will grow it by the factor of alpha. Yeah.
Exactly. So now you notice that all our correctly classified records, you see them. These are them. All of them, they'll have the same new weight, but the one that was wrongly classified will have a different weight. Like he's explaining, like Bestman is explaining, when you use an exponential or a negative number, it will decay it. But when you use a positive on a positive exponential on a number, it's going to grow it. And that's why the wrongly classified error now has a big, has its own new weight.
Yeah, bigger weight.
Bigger weight than all the ones that were clearly classified. Again, remember, our target is to point out the records that have not been well classified. Like we are still going. That's why, again, all this math has been factored into that algorithm, okay? So you just need to understand how the algorithm functions. So don't start thinking that you have to go and sit down and start typing all of these things. No, we are just explaining to you how that works. Now, the next step after you have assigned the new weight is that if you notice, if we sum all of these, it will be 1. But if you sum all of this, it will not be 1. So we need to find a way to normalize the data. Is that clear? If you sum this plus this plus this plus this plus this, if I sum all of this will be 1, 2, 3, 4, 5 divided by 5, it will be 1. But if you sum all of this, it will not give you 1. I think when I summed it, did I even add it did I add it here? Oh yeah. If you sum all of this, it will give you, so let me see. When you sum it, you get 0.8004, not 1. To bring this sum equal to 1, we need to normalize this weight by dividing all the weight by the total sum of the updated weight. That is 0.04. So if you sum all of these, if you sum the old weight, all of the old weight, it will give you 1. But if you sum all the new weight, it will not be 1. So then you need to normalize the data to bring it down in such a way that the weight can get down to, so that when you normalize it, you bring it down to 1. So but how do you do that? It's just dividing by the total sum of all of this. So the total sum is 0.0, 0.8004. So we are going to divide this by 0.8004, 0.8004. All of this will be divided by 0.8004. I think I illustrated that down here. If I'm not mistaken. Okay, yeah. You see? So I divide all of these. For those who are quick, if you can quickly sum all of this, just to be sure, I did that just to reduce the time that we have to spend in class. If you sum all of this, it will give you 0.8004, the new weight. That's what I'm saying. But if you can sum it, that's fine. But to reduce time, I already did that. So I'm now going to divide. The reason why I'm dividing is because I'm normalizing the data. That's the reason. You have to normalize the data. And so we divide. So this first one will give you 0.1254. So all the other ones will give you 0.1254. But this one is going to give you 0.4982. So that's how far we've gone. That's we're just normalizing the data, okay? We're just normalizing the data. We did not do anything here. Just normalize the weights, the new weight. Okay, now we need to make a new data set to see if the errors decrease or not. For this, we will remove the sample weight and new sample weight column, and then based on the new sample weight, we will divide our data into buckets. Awesome. We need to create buckets. I'm calling them buckets. Let me call them buckets because that's what you easily understand. So when you say buckets, it's like a range, okay? We need to put each record into a range. So let's see. Look at what is going to happen. I used to love this step when I was looking at how this algorithm works because it's so intuitive and nice. See, when you do this division, this 0.1 divided by all of this, you are going to have 0.125, all of this. So now the first bucket will be from 0 to 0.125, this one. And so the second bucket now will be from this one to this one times 2. If you take 0.125 plus 0.1254 again, if you multiply this number by 2, it will give you 0.258. So that will be the upper value of the next bucket. The next bucket will take from here to the next upper value. So you add this number to this number, it will give you the next upper bucket for this one. And then you add that again to this number is going to give you the next upper bucket, and only that at the end of the day, you see that we are getting our buckets will run from. So you see, we're going to run from. So when you add this, I'm explaining again. Let me explain again. We have calculated the new weight. That was the first thing we did. We first of all take our old weight. We calculated we had the old weight, which is 1/5, 1/5. After the old weight, we calculated the new weight based on the formulas we have seen above. After calculating the new weight, we need to normalize the new weight so that at least when you sum all the new weight, it should have it should equate to 1. That's the normalization process. And if you normalize it, that means the new weight will now be 0.1254, 0.1254. This will be the new weight, this like this. This will be the new weight. I'm just leaving this formula here so that you see what will happen before you add that value. Now, the next thing is that you need to create buckets. So your first bucket will be from 0 to the first value. The next bucket you add this value to the value of this bucket to the top point of the previous bucket. The end point of this previous bucket was 0.125. You add this one to this one, it's going to give you 0.25. The next value is that it starts from here. And so what you do is that you add its own value to this end value here. So it's going to give you 0.3, blah, blah, blah. So what you do is you add this value to this value, is going to give you the endpoint of this other pocket. So it's now from 0.376 to 0.874. The next bucket is that you are now going to add this value to this top value here. So this is how we are creating it. So it's some sort of a range, right? So you have your first bucket 1. So you have 0 to 1.254. So this bucket, you have the next bucket. This bucket ends at 1.254. So the next bucket will start from 1.254, 1.0.1, no, this 1.254. 2 is going, where will it end? it will end where you take the value of the next record and add it to where this one ended. So if you take the value of this, the weight of the next record and add it to the end of the other, to where the value of the other bucket ended, the maximum of the other bucket, it will give you where this one is supposed to end. So if you add this to this, you are going to get this. So that's how you get a bucket. So we are going to have 0.2508. And we are going to do that for all the records to get all our buckets. Let me ask, does anyone not understand the concept of creating this bucket?
No, what is called, what's the definition of bucket? Is this the definition of bucket? That's one. I know the math, but only my bucket. Bucket
Again,
is
I want you to understand the intuition, because I'm now going to show you the implications of what I'm doing. But for the sake of understanding, I want to give it my own name. You can call it your own thing. You can call it a range. You want to call an interval, but when I give you the intuition behind it, then you understand where I'm coming from, okay? Are you getting me? Focus on understanding the rationale. When
yes.
I call it when I call it bucket, I'm saying I'm creating buckets because I want to show you how this weight that have been applied to this becomes magnified or becomes magnified or becomes replicated into identifying the records that need to be where the next algorithm needs to focus on.
Oh, okay.
You understand? That's why I'm talking about buckets. You can call it anything.
Okay.
But I just wanted to tell you how I came up with this 0 to 1 point, that all of that. But let's focus. So now let's just see. These are our buckets. We created our buckets. Don't mind the name. It's a bucket. Just call it a bucket. Okay, now. Now we're almost done with the algorithm. So that's a selection random numbers. So now what the algo does is that please listen, this is not, if they are 1 million training data, if your data had 1 million records, after this step, what the algorithm will do is that it will pick random 1 million records. Are you understanding? I'm saying that if your data had 1 million records, it will pick random 1 million records between 0 and 1. Random 1 million numbers, sorry, between 0 and 1. You know there are endless numbers between 0 and 1. Are you with me? If you had 1 million records, if you had 1 million records in your training data, once the algorithm is done with this step, it will pick 1 million random numbers. The number should lie between 0 and 1. Oh yeah, in our case, we had just 5 records in our training data. Oh yeah, some people should give me numbers. Best man, give me your own number. Any number that lies between 0 and 1.
You're talking about probability of the numbers.
Give me any random number that falls between 0 and 1.
0.2.
Okay, 0.2. Thank you. 0.2. Oh yeah, next person. Dr. Tony, give me your own number.
0.261.
0.261. Next.
0.4.
0.4. Next, we have to have 5. 1, 2, 3. We have not have 5. We need 5. Next person.
0.3.
Random numbers. 0.3.
0.3.
Last, how many? 1, 2, 3, 4. Last number. Last number.
0.7.
Oh, 0.7. Okay. We have picked, how many numbers have we picked? 5 numbers. So if your training data had 1 million, you will pick 1 million numbers, okay? The algorithm will pick 1 million numbers, but our own had just 5. So let's see. In which bucket does 0.2 fall?
The second bucket.
0.2 falls in the... No, this one ends at 0.1, best man.
Second bucket.
It should. So this one is bucket 2. This
No,
is
0.2.
0.2.
Yeah, 0.125. Okay, sure.
The next number, in which bucket does it fall in?
Still the second.
This one is 0.26. This one is 0.25.
Third
The
bucket.
top here is 0.25. So
Third
it falls
bucket.
in this bucket,
Third bucket.
right? Next number, in which bucket does it fall?
Fourth bucket.
Fourth. The next number, in which bucket does it fall?
Fourth
The
bucket.
third number falls in which
Third.
bucket?
Fourth.
Third
The
Third bucket.
0.3 falls in which
Fourth.
bucket?
Third bucket.
Third.
It's in the third bucket. So the last number falls in which bucket?
Fourth.
Fourth bucket. So we have 2 here and we have 2 here. Now, what the algorithm is going to do is that it's going to now let me use I picked my own random numbers. I've explained. Let me show you. I picked my own random numbers when I was doing this example. Let me just use that to explain. Then we'll do the illustration and then I'll show you the application. So I just picked my own random numbers, right? I chose suppose there are 5 random numbers and algorithm can take. I chose 0.3, 0.2, 0.9, 0.4. I just pick random numbers, just like you have picked, right? And so now we will see where these random numbers fall in the bucket, and according to it, we will make our new data set shown below. So now, if you follow my own random numbers, you see that I pick 0.38. 0.38 falls in this bucket, is in the fourth bucket, right? 0.26 falls in the third bucket. 0.98 falls in the fourth bucket, in the fifth bucket. Then 0.40, it falls in which bucket? In the third. 0.4 falls in the third bucket. In the fourth, sorry, 0.5 falls in the fourth bucket. So in my own, 3 records fell in the fourth bucket, and then 1 in the third, and then the other one in the fifth bucket. So what did I do? I just maintained the record for the fifth bucket. So where is the fifth bucket? So you see, you had where's the fifth bucket? You had 40, 500, male 46, 500, yes. Male 46, 500. Okay. So now let's take the first random number. This first random number fell in which bucket? Well, it was in the okay. The first random number here, which is 0.38, fell in the 0.38 falls in the fourth bucket. So I'm going to replicate the fourth bucket here. You understand? You remember the fourth bucket? This is the fourth bucket. Female 40, 600, yes, 150. 1 blah, 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 blah. So that is why I said if you had 1 million records, you are going to do this one, you are going to pick random 1 million numbers. And according to the position of the numbers that you have picked, that's how you are going to be doing your replacement, okay? I'm going to come back to the numbers that you people picked, and then we're also going to develop something similar. So let me follow this one. So my first record fell in the first bucket. So the first value here, I'm going to replace it with the fourth bucket. Is that clear? With the data from the fourth bucket. I'm generating a new data set, okay? It's not like I'm replacing. So I'm generating a new data set. Sorry. It's not like replacing. So I'm creating a new data set. Some sort of creating a new data set, yes. Exactly. But the new data set is coming from the old one. So the next number, undo. Let me undo. The next number, this one, 0.26 falls in which bucket? 0.26 is in which bucket? 0.26 0.26. It should be in the third bucket, right? So you see my next record will be the third bucket. The third bucket says that what? 42, 2,500, no, female. Where is it? Is it in the third bucket or in the second? Which bucket do I have here? I have it in the, is it in the second bucket or in the second bucket? 0.26. Where are my buckets? Where did I put my bucket numbers?
It should
Yeah,
be in the
exactly.
Ah,
Because I'm wondering whether
I
okay.
actually had a column called buckets now. Have I mistakenly deleted it? Sample with, oh, Boris. I actually created a bucket now. Did I mistakenly delete something here? Well, let me. I created buckets now. What in heaven? Am I the only one who was seeing this thing called buckets?
We
Yeah,
have
there was
bucket.
bucket and
There was a this thing with buckets, right?
yeah, the last column.
Oh, la, 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 la.
So
Now I'm not seeing it. I don't know whether I've deleted it. Okay, anyways. Let's just see this second value. Let's see where this second value is going to fall. 0.26. 0.26. This one is going to be, see, this is going to be difficult because I've not seen. So let's maybe assign. I have to explicitly create this thing now and again manually. Got it. So if you take 0.12 plus 0.124, what is going to give you? 0.124, sorry, not 124, 125 plus 0.1254 is going to give you 0.2508, 0.2508. So 0.25, so this one will be 0 to 0.1254. Let me clean this thing so that we do not get an error here. And then this one is going to be 0.12542. The maximum value here is going to be 0.2580. 2508. Okay.
Yes.
2508. So if I come and seek my second value here, what was my second value? 0.26. So it's not yet in this bucket. So because it's 0.25. So the next one is going to be from 0.25. So when I'm going to add, can I shift it up so that they can align? So that should not be that I'm now calculating. So let me calculate the next one. I'm going to add 0. So if I add plus this value now, I have to add this value to it, this one. So if I add that value, I'm going to have plus plus 0.1254 again. This is going to give me 0. So this one is giving 0.2508 to 0.3762. So when you do that now, this gives you in the third bucket. So we have our random numbers. Random numbers would have been, okay. So now we have 0.3 0.26, so it should fall in this bucket. Let me see. Should it fall in this bucket? Yes, it should fall in this bucket. 0.26, yeah. should fall in that bucket. 0.26 should be in the, should definitely be in the third bucket. So if I come down, where did I put it? Did I put it in the first or the third bucket? I definitely left it in the second bucket. Why would I have done that? Why did I leave it in a bucket? Did I round up this one? Why would I round it up? Because I'm replacing it here with the second bucket instead of the third bucket. Let's see. Let me see the next one. This one goes in the fifth bucket because it's 0.98. So the fifth bucket is, I replaced the fifth bucket with, was I following the positional argument to replace this thing? It was supposed to be done like that. I don't know. Let me look again. 0.4 goes into 0.4. 0.4 goes into the fourth bucket. Let me see that. I think I just mixed up the whole thing. I don't know where that bucket calculation file went to. I had another copy of this file somewhere. Oh, please let me pull it up in my Google file. I don't know. Something just changed with the file. I don't understand why. Let me open Google Colab. I think I have that file somewhere, but I don't know where it is. Trust me, shared with me. I have to look at. So, oh, the whole file just changed. There's folder. I had weekend classes. Where's that? Wait, let me come down to weekend March. Is this my Google folder? Yes. Weekend 11:30. Weekend notes. Yes. Machine learning. Yeah, no. Decision. I have ensemble technique theory. Is this ensemble technique theory? Let me open this with Google Colab and see where I messed the whole thing up. For some reason I surely messed my own file up. I don't know. Please hold on. This is the thing. This is not the file. Boosting technique. Oh la la, it did not, this guy did not plot my graphs. That's bad for you, bro. Let me download it. It will not bring up my images. If I hold you in my hands. Oh no, 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 no. You are plotting on and I doubt whether this guy will do the job. This guy too has not done the job, so I have to directly bring it up into. Oh, like, I hate this kind of that I'm doing right now. I have to come to Champions Large Machine Learning. Let me upload it. Immediately, please. Downloads. Wait. Load. So why is it showing? I hope this guy would have run those images. So, is this the same file? These images are not being drawn. I don't know why. They are supposed to pop up. So, hold on. Oh, it's not plotting my image. It's not bringing in my images that are imported. Oh, and the other one just got distorted, and it's not drawing all the images. Why is it reading the images like this? What changed? Is it? Nope. Oh la la. Anyways, let me just go back to this one that was all distorted. Don't know what happened. Trust me, I don't sabi what changed. The same file that I have with this thing now, I'm opening it that way. It's not even showing me the thing. I don't know what changed. But let's come back and let me explain what is going to happen. So going back to the explanation we were having. So once the algorithm picks up the random numbers based on the number of records you have on your training, it's going to now take the first number. Boom, which bucket does that first number fall in? If it falls in the first bucket, if it falls in which bucket, like this one, it failed in the fourth bucket, you have it on the fourth bucket. It just creates a record of the fourth bucket. The next record, where does it fall? This one falls in the fifth bucket, it creates a record of the fifth bucket. This one, where does it fall? It falls in the third bucket, it creates a record of the third bucket. And so it's going to do that for all the records. And in this case, you notice that 3 of our records were in the fourth bucket, which was the record, the bucket that was misclassified. And if we use the examples that we had here, if we use these examples that you gave, that means our first record would have been in the 0.2, would have been 0.2. 0.2 would have been in the, oh, it's because I see why I put this one here. Because this is 0.26. And that other one, if you take it to 2 decimal place, okay. Oh, I see why. Okay. So you see, if we follow this one, 0.2 would have had 0.2 somewhere around the second bucket. So it would have, if our first record would have been this record, the record of the second bucket, this would have been our first record in the new data set. Then you look at 0.261, 0.261 would have been the third record. It would have been the second record in our new data set. This would have been our fourth record. So it would have been the next record in our data set. And then this one again would have been the fourth record again. So it would have still been this one twice. And then 0.07, 0.7 is the fourth record. So it would have been the fourth record. So if we would have used this, our own randomly selected numbers, we would have had the fourth record appearing 3 times. And then second record appearing once and third record appearing once. So our final data set would have shown this record, and then 3 of these records. I don't know if it's clear.
It's clear.
If we are following these randomly selected numbers that you gave me here, you notice that this number would have been in the second bucket. So we are going to take this in that new data set. We are going to take this record and put in that new data set. Then we go again, we pick this number. This number will be in the third bucket, this bucket. So we are going to pick this record now like this and put in our new data. Our new data now has had 2 records, but we need 5. So we go to the third number now. The third number falls in this bucket. So we pick this record and put in as the third record in our new data set. This record again will fall in this bucket. We do the same. This record again will fall in that bucket. We do the same. So you notice that we now have had 5 records in our training data. And these 5 records will be made up of this one, and 3 of this one. Now, you notice that because of the fact that the weight of the error, the weight of this record that was wrongly classified is higher, the probability of a random number falling in that range is also higher.
Oh,
do you understand
that
that?
explains the smooth algorithm I was talking about, where the weights kind of make the model look at certain data points more than others. Similar.
Great. So you see that because that record was wrongly classified, how it highlighted it was just to make it come up multiple times. That is why when you come down to the final data set, this is the data set that we now have. You have the record that was wrongly classified highlighted 3 times. And then these ones were clearly classified. So what is going to happen now is that this is the data set that's going to go to model 2, this one. Not this one up again. So it's this one that will now go to the second model. Now you notice that as the second model is trying to classify, it will focus. You see that in a sense, more of its energy will be focusing on trying to classify these records. And now it will do its own job and then identify through the same means again. It's going to reassign weights and then send it to the next record, only like that, to the next model. And that is going to be the process. And that's why each model does a split just once and then highlights the errors, sent to the next one, only like that. So if you are 100, if there are 100 models, that is going to be the process that's going to go through for all the 100 models. Is that okay? But you don't manually manipulate these things. Once you bring down the Adaboost algorithm, all of this is going to come into play. Is there any question?
Question.
Yeah.
Yes. Yes, best man, you say you have a question.
Yes. So at the end of the day, the classification made by all the models, if there are 5 in number, let's say there are 10 models, are they going to average out the error? And what will be the final linear separation? Is it going to be
Now
an aggregation of all the linear separators or
that
the
is a very
vectors
good
produced?
question. You are now asking a very good question. We'll get there. Let me get Mr. Tony's question, then I'm going to answer your own. You are now asking me, how then do I make prediction? Is that the question?
Yes.
Good. Thank you. Mr. Tony, you had your own question. We'll
Yes.
come back to best man's question.
Yes, I mean, since these tend to be, I mean, with the way it functions, tend to be a bit weak or something. So, in what areas do we apply, or can one apply this algo boost technique?
This boosting technique is one of the best techniques you'll find out there for modeling. I'm telling you the truth.
Oh, really?
Boosting, it performs well, performs extremely well, right? And so in this our case, we were taking a classification situation, for example, right? A classification situation because we are classifying. So if you have a classification situation, but then you know that the decision tree we are using here is a decision tree classifier. I said this in our last class. Because it's classification, we are using a classifier. If it's a regression problem, you'll be using the regressor. Did we say this in the last class? Remember, I said this in the last class. That if your problem is a regression problem, you use the decision tree regressor. And if it's a classification, you use the classification regressor. If you mischange it, you get an error. So to answer your question, Mr. Tony, you find this very performant, where when we do the practicals, you'll see. We'll do the practical, we'll run a normal decision tree, right? And we might even run a normal decision tree, we'll run random forest, then we'll run Adaboost, then we'll do all the other boosting techniques, and then you test, you see, it actually performs well. So again, you can use it depending on your problem that you want to solve, but just make sure that most of the time the ensemble technique really helps because you want to run it across, you try different models and see what you get, where you get the best performance. In machine learning, it's not like it's casted that you must do this. No. When you have a problem at times, you want to try different algorithms and different approaches to see which algorithm works. And then you try to twin, right? You try to twin, like you remember, hey, nobody ever returned me the result of that hyperparameter tuning that we did in the last class.
You know, if I didn't have the computing power.
Even if it took 20.
I sent it to you. I sent it on the group.
You should have reduced the range. You said you shared best man.
Shared on the WhatsApp.
You should have reduced the range because we were running the range from this to this. Why not reduce the range? Maybe instead of running from 1 to 10, you can run from 1 to 5 just to get the result, right? Madam Pierre, you were one of the persons who was actually following the class actively. You did not send me anything.
My computer started hanging, so I left
it. You can go and change the range, like Bestman was explaining. You can change the looping range and reduce it maybe to 2, or maybe just something just to get the result.
You have to reduce the complexity because the parameters they're so complex. So if you include too many parameters in different dimensions, it's going to be compute heavy. You want to fix other parameters fixed and then iterate on one parameter or a couple of few. When you now get optimal, you now take the optimal parameter and fix it. Then now you now go to the next parameter and layer and give the other options. That's where you can iterate on them and get the optimal parameter. If you put all of that at the same time, it's going to take a lot of compute
and run
time.
you need power to be able to run it. Okay. So you can please you do that and send me screenshots of your results in the group, please. I'm going to look at what Desmond said. I'm sure I missed it out. So okay, now to best math question. The question now is which algorithm do we use, or how do we do prediction? I think I answered that question somewhere up here. When I was talking about alpha, I think there was a thing I say. Basically, we are checking. No, not here. How prediction is done. Prediction H1 alpha plus H2 alpha plus H2 to the alpha. Here, H1 alpha is the prediction done by model 1. Here is suit for binary class. Here 1 for yes and no for 1. So if prediction is negative, then no class else, yes. Okay, now you use the amount of say to be able to do prediction, right? And now let me come up and show you people something. If you notice, right, the algorithm where the alpha value is least is the algorithm whose prediction will be taken into consideration. Where's the calculate alpha again, my people? Yeah, it did not show you where we call it. Where is that place again? Did we lose it again? Okay. You see, now if you notice this, it takes into consideration the amount of error. Is that clear? And so the algorithm with the least error will be the algorithm where your alpha is actually going to be. Is it actually going to be the highest, or is it going to be the lowest? The amount of, say, the algorithm with the highest alpha, with the highest alpha, where your alpha value gives the highest significance, is the algorithm that is going to be used. And that is why it's going to be used for prediction. That's why I said something over here. See, let me come up and show you. And definitely it's going to always be the last model. Let me show you something, a statement I made up here. So here, it is a technique to build the strong classifier from weak learners. So you build a strong classifier from weak learners. So this weak is not well spelled. This is how to spell weak now, boys. What's wrong with you? Oh, wonderful. So you use weak learners to do. So the final model will always have a better alpha value. You understand? And that will be the model whose prediction will be used during testing. I don't know if that answers your question, best man. Because when you know that alpha gives you we call it the amount of C. I keep saying it's the amount of C. It's so which model it is that at the end of the day gives the best alpha value, something like that.
Yeah, that means the models are in sequence and they run.
Yes, it's a sequence of models.
To be the tail models, the one at the end.
The tail, yes. Exactly. So that's how prediction is done based on that model. And so once you run it automatically, that is the model that takes it into account. And that's how the framework does that estimation. I don't know if there's any other question.
Does it have timeout? Like if you've gotten the optimal, maybe the error is within your threshold, can you stop? Does it have a stop? The boost, does it have a max, like can it declare and run out? Rather than you just run if you have 100 models. If you have done the answer in 50 models and you've gotten 0 point something, a minimum error, would you want to go through all the models, or you can just terminate itself?
So what I noticed from my experience was that because what I used to do is I just twin and change the total number of models that I want to use, right? Are you getting me?
Yes.
Are you there? Yes.
Yes.
So what I noticed is that once it gets to the point where the values, the model is where the error most of the error has been handled. Let's say the error is least. You notice that the prediction from all the models is almost always the same. You understand? If it's for the case of a
Okay.
categorical variable, you'll notice that it becomes recurrent. You understand?
Okay.
Becomes recurrent. If it's the case for a logistic regression, you know, or a logistic problem, you notice that the error between the predicted values, the difference, sorry, not the error, the difference between the predicted values is always close to insignificant. Like the values are always almost the same. We just a slight difference in between them. And so when you see that what you might want to do is that you might want to retwin, you might want to twin that algorithm, the number of algos that you have used again, and keep testing till you get the best balance. You understand? So it's not like you will tell you that, oh, I'm out of errors. You get it? Because in real sense, it's not like say out of error per se, you get it. You just keep
Okay.
highlighting. But then
Okay.
there will be no significant difference as far as the prediction is concerned. The outcome is concerned. Is that okay?
Okay. Yeah, it's fine. I think it will become clear when we implement. And if you can add the maths
Yes.
to it for the entire model, is there a maths in this the maths to it, so the entire model?
I just added them
a
formulas,
mathematical notation.
formulas.
Yeah.
I just added these formulas and all of that on how to calculate the new weight and all of that.
Not in a closed
I have
form.
to leave you guys now.
Okay.
Yeah, I have to leave you guys now. I have another class. We'll have this. Oh, let's talk about this thing tomorrow, gradient boost tomorrow, and then we join the practical, all the boosting practicals together. Okay. And then we just do all the boosting practicals together. Does it make sense? Because boosting, the other gradient boost is almost the same, but there's just a slight difference. So it's good that we just hammer that tomorrow, and then we just do all the practicals together, and then we see how it works. Okay. Okay, let me leave you guys. I have another batch to teach now, and then I'll see you tomorrow, same time. So I'm hoping that next week we can go back to our old schedule, so that because this is really affecting a lot of people, I don't want to keep putting people on a tight end. But I'll try to see how to work on my program. I'm still getting some challenges, but I'll see how to work on that so that we can go back to our old schedule. Okay, thank you guys very much. If you have any questions, please, the chat groups are there. Please share your challenges there. Let's have discussions there. Hey, best man,
Yes.
look into the predictions again. Send things around alpha, what the weight means. In short, how do we use the weight to now come up with the final prediction? All of that, please share in the group so that we can keep learning. Okay.
If I'm away, I'll share. Thank you.
Okay, you can share after when you are home and stable. Okay.
Okay.
See you all tomorrow, same time. And we'll talk about gradient boost and possibly XG boost. And then we do the practicals in the next class. Okay, bye-bye.
Mm.